All right, let's do some fun problems. We got 3 examples. Find the derivative. Find h prime of x for h of x equals 3 to the x over 3 to the x plus 2. All right. So again, we could use the product rule if we wanted. We could write this as a product instead of a quotient. This one, I think the quotient rule makes a little bit more sense. So our top function is 3 to the x. Its derivative, the derivative of any exponential function is itself times the natural log of the base. And g is the denominator, 3 to the x plus 2. The derivative of any exponential function is itself times the natural log of the base. Derivative of 2, that's a constant, so the derivative of a constant function is 0. Derivative is the slope. All right. So the slope of an exponential function is the function value times some constant, the natural log of that base. So anytime I use the product rule, I really like writing it out. Low d high minus high d low, square the bottom, and away we go. And now we just substitute. F prime is 3 to the x times ln 3 times g, which is 3 to the x plus 2, minus f, which is 3 to the x, times g prime, which is 3 to the x ln 3, all over g squared. 3 to the x plus 2 squared. And just like most of the times when we use the quotient rule, really the big fun stuff just happens from after the calculus. The big fun stuff is just simplifying just the algebra afterwards. So let's what do I want to do here? We're gonna have to distribute from the first one. The second one doesn't need any distributing actually. So let's look at this algebra right here. Multiply this together. 3 to the x times 3 to the x. You're multiplying two exponentials with the same base. You just add the exponents. What's x times x? Sorry, what's x plus x? 2x. We still have the natural log of 3. So that's this part of the distributing. Now we need this part of the distributing. I'm going to make a mistake and I want you to watch for it. So don't write this down. Multiplying 3 to the x ln 3 times 2. This is wrong. What did I do that's wrong here? Distributing right here. 3 to the x times 2 is not 6 to the x. Okay? It's 2 times 3 to the x. It's very, very different. So watch out for that. It's a very easy mistake to make. These can't combine at all. 2 times 3 to the x. They can only combine if they both have an exponent, the same exponent. All right, and the denominator, we could FOIL out if we wanted, or we could leave it factored. Usually, for fractions, we like to leave things factored. And in that same vein, we're going to factor our numerator. So we're going to take out what they have in common. They both have a natural log of 3. And they both have a 3 to the x. When we take a 3 to the x and a natural log of 3 out of here, we're only left with 1 3 to the x left. And we take out a 3 to the x natural log of here, we only have a plus 2 left over. Oh, something really nice is going to happen. Look at the top and the bottom. Also, we really could have just factored that out in the first step. If we factored out in the first step, it would have been a little easier, but wait, if we factored it out in the first step, 3 to the x ln 3, we'd have been left with a 3 to the x plus 2 minus a 3 to the x. Wait, why am I losing my mind? If we factored out a 3 to the x ln 3 at the start, we'd be left with this minus that. How is that different than what we have now? Oh, because I'm missing a term. Ha ha ha. So I distributed, but we still have this term from before, right? I have a package. I grab my package right now. Yes. So we still have that last term. 3 to the 2x ln3. Be right back. All right, we're totally back here. Where was I? Oh yeah, we added that last thing, and we're factoring out a 3 to the x ln3. So there's also that third term that we're certainly not forgetting about, and that's going to be left with a 3 to the x when we factor out a 3 to the x ln3. So something nice happens, just like I said, but it was something different than what I expected. So we have 3 to the x times the natural log of 3 times what's left over, just a 2. We're going to write the 2 right here. We didn't have to factor it at all, actually. We could have just, we could have actually just combined it in a different place. But yeah, here's what we have. I'm feeling very nervous about this one. I definitely want to check my answer on this one, since I did already make a mistake in trying to find it. So again, what's one of the easiest ways to check your answer is plotting a tangent line. Let's plot this function. Okay, our function that we're looking at is 3 to the x divided by 3 to the x plus 2. Let's look at a tangent line when x is equal to 1 or something. It'll be y minus 1 equals a slope times x. Sorry. If this is f of x, right? What is f of 1 when x is 1? 0.6. And then we just need to find the derivative here. So we're saying that our derivative is some function 2 times 3 to the x ln 3, all divided by 3 to the x plus 2 squared. So we're saying that the green function is the derivative of the blue function. And again, even before plotting the equation of a tangent line, we can kind of look at this. Look at the blue function. The blue function should have a slope close to 0. That's positive. And then it should get bigger up until here. Yep. Slope is 0. Slope is getting bigger. Green is our slope function. And then again, it's still positive, but the slope gets close to 0 again. So it actually looks pretty believable. So what is the slope of our function when x is equal to 1? About 0.2637. All right, so then what remains is to graph this and zoom in and say, well, does this look like the tangent line at 1? And we're going to have to zoom in on the y coordinates as well. See whether this looks like a tangent line. Really going to have to zoom in. It's kind of hard to see. Yeah, it looks like a tangent line. Sure, great. All right. That's one way to check your answer, even for like a general function, if you are feeling nervous. Look at the relationship between the function and its derivative in general, and you can also plot a tangent line. Luckily for me, in the next example, it's asking us to find the equation of a tangent line. Find an equation of the tangent line. To y equals log base 2, 3x plus 1. That's parallel to the line y equals 1/2 x plus 5. So right off the bat, parallel. That means same slope. So the slope of our tangent line has to have this slope. The slope of the tangent line is the derivative. So the derivative has to have this slope. I slightly changed this problem. I made it a little harder, but it's okay. So if we do this, right? Just say, when is the slope equal to 1/2? Well, we have to find the slope. The slope function is the derivative, and the derivative, well, we'll have to calculate it, but the derivative of a logarithm is the reciprocal with the chain rule and with the natural log of the base. The natural log of the base goes here. Chain rule goes here. And yeah, we're going to have to approximate a little bit. Thanks, Jason. Now we want to know when the slope is 1/2. The slope is 1/2. Slope of the tangent line is 1/2 when the derivative is 1/2. So set it equal like so. And we'll have to do a little bit of, it's going to be a messy answer, but this is how we can work with it. Solve for x. We can cross multiply to start. 3x plus 1 times the natural log of 2 equals 6. Solve for x. Divide both sides by ln 2. Subtract 1, divide by 3. So that we can also just divide everything by 3. Depends on how you want to approach this problem, or you could just have a 1/3 out in front. So this is our exact answer for our x coordinate. We can often use, times we do want to use the exact answer, but I'll try to specify whenever I can. Here, let's approximate it. 2 over ln 2 minus 1/3. That's about 2.5521. So this is the location, right? We're looking for an equation of the line tangent to this function that's also parallel to this other function. So we said, okay, here's the slope of our function at any point. We want to find when is the slope of this function equal to 1/2. And we found that it was about 2.5. Now, we just use point slope form. We found the x coordinate. X coordinate is about 2.5521. We have to find the y coordinate, and we already know our slope is 1/2. So our function, right, is log base 2 of 3x. Again, this is what our x naught is, plus 1. Type that into a calculator. Log base 2 of 3 times x. And you can put some extra digits here if you want to get it even more accurate. Plus 1. It was plus 1, right? Yeah. That's about 3.1137. So if we graph our function, which I actually haven't done yet, we graph our function, log base 2 of 3x plus 1. We're going to have to reset our scale a little bit. Again, you can, whoa, wrong button. You can click on this wrench here. I usually have it a little zoomed in so you can't see it, but click on the wrench. That opens up this menu to set our scale. We're looking when x is equal to 1. We're going to have to zoom out a little bit. Great. And we think it's going to be y minus that y naught equals the slope times x minus that x naught. Oh, not when x is equal to 1. This is what we think our tangent line is. And look at that. That looks like a tangent line. The last thing that we want to check is this tangent line parallel to the line they gave us? It's supposed to be parallel to the line y equals 1/2 x plus 5. Is pink and orange parallel? Yeah, they look to be pretty parallel. Great. Last problem in this video. Everyone's favorite little guys. We're going to talk about mosquitoes. A colony of mosquitoes has an initial population of 1,000. Initially, there's 1,000 mosquitoes somewhere, hopefully in a large area. After T days, the population is given by A of T equals 1,000 e to the 0.3 T. So again, exponential functions, AE to the BT or RT. R is that rate. It's positive, so we have a growth rate of about 30%. A, that's our initial value. Initially 1,000. Whoa, Jason, what is going on up there? What's going on up here? This is what happens when I talk at the same time as writing. All right. So, interpreting exponential functions, that's what's going on here. And again, a small side note, we say the growth rate is 30%, but that doesn't mean they grow by 30% every day. If they were only growing once a day, then those would be equivalent. But because this is continuous growth, remember compound growth versus continuous growth. Since it's continuous growth, they actually grow by more than 30% every day. Even though we say the growth rate is 30% every day. It's a little counterintuitive, but we feel free to ask me about that. I can talk about that some more, but I don't want to do it here. So this is the growth rate. Let's ask the question. Show that the ratio of the rate of change of the population to the population itself is constant. So it sounds like a big ask, but it's not that bad. Let's read that question again. Show that the ratio of the rate of change. What's the rate of this change of this function? A prime of t. Show that the ratio of the rate of change of this population is the population itself. Or sorry, rate of change of the population to the population itself is constant. So we just need to find this ratio, the ratio of A prime to A, and show that that's equal to a constant. All right, so let's just copy down this formula and find the derivative. When we take the derivative, we have a number times a function. We can use the constant multiple rule. It's going to be 1,000 times just this derivative. Derivative of an exponential function is itself times the natural log of the base. We don't have to use the natural log of the base here. That's 1. Natural log of v is 1. Times the derivative of the inside. The derivative of 0.3t is 0.3. So this rate of change function, our slope function, our derivative is just 300 e to the 0.3t. This gives the rate of change every day. This shows how many mosquitoes per day we're growing at. So at the start, when t equals 0, this whole thing becomes 1. At the start, we're growing by 300 mosquitoes every day, approximately. And that should make sense, right? If our growth rate is 30% and we start with 1,000, we would expect about 300 mosquitoes to grow in that first day. And again, it's not an exact answer. That's the slope of the tangent line, which we talked about as being an approximation for the actual growth in a day. And again, the reason it's an approximation is because we're only looking at the tangent line here. So it's an approximation very close to the start, but the further into the future we go, right, the bigger the difference between our approximation, that tangent line, and the actual value, the exponential function. All right, so all that we're asked to do is look at the ratio of the rate of change to the population itself. What's the ratio of the rate of change? This is the ratio right here. What is this ratio? Well, the top, we said, wrong color, Jason. The top, we said, was 300 e to the 0.3t. And the bottom is the original function, this guy up here. That's 1,000 e to the 0.3t. What's this ratio? Let's simplify. We have an exponential, the same exact thing on the top and the bottom, that cancels. All that's left is 300 over 1,000. That's 3/10. 30%. 0.3. Oh. Show that that ratio is constant? Well, yep, that's a constant. We did exactly what we were supposed to do. We showed it. That's one of the big things about exponential functions. There's a bunch of big things about exponential functions, but we're going to stop here for this video. And the next video is a really good one, so make sure you're prepared. Get your water, get your stretches in, get your mind relaxed, because logarithmic differentiation is coming up next, which is really powerful, really cool, really fun, and sometimes a little messy. Bye-bye.